Okay, so now let me report on progress made in my work package, which is new morphisms of graphs. Since we are a little bit behind time, let me be really at meteor speed when it comes to recall, so that then I can be with a car speed when it comes to the new stuff. So I'm talking morphisms of graphs, and we have two types. Basically, we have the usual homomorphisms of graphs, which map vertices to vertices, edges to edges, preserving the endings and the beginnings of the edges. But we can do something more fancy, and it's actually needed in real life, so-called path homomorphisms of graphs. So here we again map vertices to vertices, but we no longer map edges to edges, and it's basically given as a map between the space of finite paths in one graph and the space of finite paths in another graph. Of course, we still want to preserve the beginnings and the endings of paths, and we have this very standard decomposition rule. Okay, let me find my highlighter. I lost it somewhere. Okay. Oh, you see? So this is kind of like having a functor. All right, so of course, having a homomorphism also gives you a map from the space of paths to the space of paths, finite paths, of course. And the way you distinguish one type of a morphism from another is that the usual homomorphisms preserve the length of paths, whereas the path homomorphisms need not preserve the length of paths. Okay. Now, let me first recall what are the conditions to ensure contravariant factoriality of the construction of graph sister algebras. And let me mention that we discovered that, in fact, Katsura found these conditions a few years ahead of us, and he found it in the context of topological graphs. And when you plug in discrete topology into Katsura's conditions, you obtain on the nose our conditions. We just were not aware of it. But it's okay. It's in a way reassuring, because now I'm very much convinced that what we found is really the best possible conditions you can have. And let me not discuss all of these conditions. I just want to draw your attention to the most important one. There are three of them. This is the target bijectivity condition. You see, now we managed to realize this target bijectivity condition in a very conceptual way, which was thanks to our secondment to Arizona. This was Mariusz Topolsky's secondment to Arizona and his discussions with John Quick that had an influence on my paper with Mariusz Topolsky. And now this is something which was not in Katsura, and it basically allows us to realize our key condition for contravariant factoriality in a categorical way. We simply say that we have that this diagram is the pullback diagram in the category of sets. If this is satisfied, well, that's equivalent to the usual form of writing target bijectivity, and this is what makes things work. Well, there's another condition, but it's very simple. And well, when all these three conditions are satisfied, we say that we have an admissible graph homomorphism. Now, how about covariant conditions as were developed by Mariusz Topolsky and myself? Again, there are three conditions. And here, the most important one is the third condition. And because it will play a role in what I'm about to say, let me be a bit more specific. But this is a very complicated condition, difficult to parse. The way presented here, it looks like written for lawyers. Although, of course, if you want to rigorously prove anything, then that's the best way to do it. Then this is what comes really handy and is really useful. And actually, a referee required that we phrase it in such a way. And we are again very happy that we were forced to do it like this, because then the proofs were really streamlined. But it's very hard to take in just a few seconds. So let me maybe try to explain it to you very quickly using a pen. Okay, I think it works. Okay. Yes, it works. Okay, so the idea is the following: you have a regular vertex with finitely many edges emitted. Sorry, I'm using my mouse because the battery of my pen went dead, so it will not be as fast. And on the other hand, You also have a regular vertex, but it emits fewer edges than here. I mean, not more edges than on the left. So here it is n edges, then here it is m edges, and m is less than equal to n. And what do we play? We play the following game. We pick up some edges here and put them into the basket. We say, okay, we are happy with these edges. And the remaining edges, we say, no, these edges are too short paths, and we extend them. But the rule of engagement is that we have to extend them always, but all edges emitted from their endpoints, okay? And then we iterate this game. Some of these paths of length 2 we put into the basket, and for the others, we say, no, 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 they are too short, we want to extend them. But again, you have to extend them by all edges that come out from the endpoints, okay? So this is roughly the idea of this regularity condition. And I realized that I should also tell you about this target bijectivity condition of what it tells you to do. Basically, what it tells you to do is that when you identify the edges, you should identify as many edges as you identify endpoints. So, for instance, if you have two edges like this, then you can map them to one edge like that, because you identified two edges and you identified two endpoints of these edges. Okay, you can also do it like this, but these are two completely unrelated edges, and you map them to one edge. Okay, you must simply have a bijection between the number of vertices identified and the number of edges identified. But what is not allowed is the lambda shape, right? Because what I do here, I identify two different edges, but only one endpoint is identified with itself. So the 1 and 2 are different numbers. We have no bijection. Okay, but this is still just a recall. And now with these conditions, we have the following theorem. So in the case of topological graphs, this first functor is, oops, I have the wrong, I wanted to use my highlighter, not the pen. Okay, so now let me switch to the highlighter. Yes. Okay. See, I also have to toggle the zoom, which makes it problematic. Okay, I had the wrong tool in my hand. Now it's okay. So that formula for the contravariant functor was written in the setting of topological graphs by Katsura, and Mariusz and I, we rediscovered it in the case of discrete graphs. But the situation is very clear. You take an edge or a vertex, okay, and you take this projection of partial isometry associated to it, and then what do? You look, remember, this is a contravariant functor. You look at the pre-image of this edge on the vertex, and it will be then a bunch of partial isometries or projections, and you sum them up. Okay, this way you get the contravariant functor from this category of admissible graph homomorphisms to the category of C-star algebras and star homomorphisms. In fact, equivariant star homomorphisms, but let's not get into details. And the formula for the covariant induction is actually easier, because again, you take an edge or a vertex, and then you have this projection of partial isometry to the projection of partial isometry, which corresponds to the image of this edge or a vertex. The only subtlety is that this f of p need not be an edge. It can be a path, all right? And this is this is a composite partial isometry. This is a sequence of partial isometries multiplied. But it defines a covariant functor, again, from this category of admissible graph homomorphisms, admissible path homomorphisms of graphs, to C-star algebras and star homomorphisms. But because these morphisms do not preserve a length of paths, the U1 equivariance with respect to the gauge action is lost. Okay, and now I begin my talk, because now this is the new stuff. What was very disturbing was that in real life applications, which we're studying pullback diagrams and understanding, say, things like non-commutative CW complex structure of quantum projective spaces, it turned out that our pullback diagrams were using both functors, covariant and contravariant. We call them mixed pullback diagrams, because what was happening was that we had a pullback diagram, but for two parallel arrows we had to apply covariant functors, and for other two parallel arrows we had to apply the contravariant functor. So this was very disturbing because the commutativity of such a diagram on the level of graphs would not ensure the commutativity of a diagram at the level of graph C-star algebras, obviously, because you apply two different functors. So this was very disturbing, but this was what was popping up in real life in non-commutative topology. So one of the goals of the project, which was to a large extent already achieved, was to find the common denominator. And so for starters, Gilles from Florianopolis, our new node, had a very nice and simple idea that in order to have all these two different categories for contravariant covariant inductions, these two different types of admissible morphisms, to have them in one bag, then we should replace maps by relations. And then we can put both categories into one bigger category, okay? So we define now a morphism between graphs as a relation in the Cartesian product of the space of finite paths in E with the space of finite paths with F, satisfying some obvious rules. So for instance, if X is a vertex, then Y also has to be a vertex if they're in the relation. If X and Y are in the relation, then their beginnings and their endpoints are also in the relation. So these are like very, very basic requirements that you put on this relation to call it a graph relation, okay? And now what you can prove, and that's what we do in our joint paper, Gilles De Castro, Mariusz Tobolski, and myself, is that for starters, we see that directed graphs with graph relations form a category, and that's easy because it's obvious how to compose relations. And now these PG categories and OG categories are its subcategories, but I write here the inverse because in this category OG, maybe let me go to the beginning and remind you what is meant. You see, so this is the OG category, and this is the PG category. Okay, ordinary graph homomorphism, path homomorphisms of graphs. So here we have to reverse arrows. It's a matter of choice, but okay, one is for covariant functoriality, one for contravariant. So one of these categories arrows have to be reversed. And for the time being, we choose to reverse the arrows in this first category, OG. Okay. Then when you reverse arrows, we see that you can very easily read these morphisms as relations. So you have subcategory here, and moreover, and this was really hard. And this happened because I went to Brazil, and then I realized that it's really essential to have Gilles as a collaborator for this project. And we were working very hard on this, and this was not an easy thing. But finally, we managed to define a category of relations, which would be admissible relations, that would have these admissible relations in the sense of path homomorphisms, and sorry, admissible morphisms in the sense of paths homomorphisms, and admissible morphisms in the sense of homomorphisms, that these two admissible categories sit as subcategories in our new category of admissible relations. And here the main obstacle was to see that it is a category. We had an issue with composability, which had to be resolved by redefining things, okay? But it's done, we have it. Better still, you see, I was pretty certain that the definition will be able to match definitions, although some of these lemmas proving that the previous cases are special cases are not at all immediate. But what makes me absolutely happy and delightful is, and also it was clear to me that now we can have the one functor defined. You see, this formula almost doesn't change, except that now what I'm doing, I'm summing over all q's which are in relation with p. Okay, so you can immediately see that this formula looks very much like the unification of the previous two formula, because it's now really, really obvious that when you write these admissible path homomorphisms of graphs and homomorphism of graphs as relations, you'll see that this formula on the nose and immediately recovers these two formulas. Okay, so that was easy, that it defines a covariant functor, but what really makes me very happy, and there's no way I can spell out the details, is now that we have a pullback theorem for Leavitt path algebras that uses the above functor, and it generalizes at the same time our state-of-the-art push-out to pullback theorem, which is about to be published in the Journal of Geometry, and the mixed pullback theorem, which has already been published in the Bulletin of the London Mathematical Society. So see, Robert, there are more publications that you listed. It's just there is no time to. I mean, sorry, we are behind in recognizing. I mean, putting them all together and having a list of publications of a project. Okay. Although I must say that these two papers are attributed to related but different projects. Okay. Anyway, what is very important is that we have a common denominator theorem for our two most important theorems in the area. So this common denominator is really working. At the time, we have it only for Leavitt path algebras. And because it digs very deeply into the ideal structure of homomorphisms, we still have to double check that we will have it at the level of graph algebras, but I'm very optimistic about it. Now, because of the new amendment, I'll be able to work with Gilles more intensively. And I believe both Gilles and Francesca, Francesca and I are coming to visit Gilles in February. So we hope to really make it work. But this is already a key achievement and fulfillment of, like, say, 50% of or 45% of my research task. What is still to be done is higher rank graphs and things like this. But what was for me my main motivation for the whole project was this vision, and it has been achieved. Now, but it would be not interesting without real life applications. So let me dwell upon these real life applications very shortly, but it's something very tangible, something that you can very quickly understand. So we have these famous Kunz algebras, which Kunz defined in 1997, and they have this very particular K theory. So K1 is 0, we don't care about it, but K0 of On is just the cyclic group Z modulo n minus 1. Okay, and the class of 1 is just 1 in this abelian group. And now from this K theory, because K0 is a functor which carries unit into unit, we can infer that a unital star homomorphism from OM to ON can exist only if the following congruence relation is satisfied. Well, it's clear how we have it. You see, if I take the class of 1 in my OM sister algebra, then m minus 1 times this one must be 0 in K0 of OM. So when I map it to the other side, since it's a group homomorphism, it also must be 0 on the other side. But to be 0 on the other side, when the congruence relation is modulo n minus 1, well, it has to be some multiple of n minus 1. Okay, so that's a necessary condition. But here we are in the realm of simple sister algebras that fall into Kirchberg and Phillips classification. And if I understood what Soren Ehlers was explaining to me, what happens is that here everything which is allowed by K theory, which is allowed, is actually implementable. But it doesn't mean that you have a formula. So in 2009, Kawamura provided an explicit formula for this for a star homomorphism satisfying this congruence. But his formula can be immediately derived, and this is like one of the very nice applications from the regularity condition for the covariant induction. So let me show it to you because I find it very nice. Okay, let me just grab a pen. Go here. All right. So you see, when you look at this formula, well, it means what? Why can't I write? Oh, yes. Then m is equal to n minus 1 times k plus 1. And instead of writing loops for the diagram of Kuhn's algebra, let me just write edges because it's simpler to draw this way. So here we have m loops. We have m of them. And here you have n. And of course, you can see from this congruous relation that m is greater or equal than n. That's obvious from the relation. All right. And now, so what do? We take first n minus 1. We take n minus 1 edges. We put them into the basket. And the last edge we extend by n loops again. And we repeat it. Again, we take n minus 1 paths of length 2 into the basket, but one we extend. Well, and when you do it k times, at the end of the day, you will have exactly n minus 1 times k paths, and you will have this one base path which goes all along, okay? So you see, the regularity condition basically allows you to guess Kawamura's formula, and in a way, it explains it. So by the covariant factoriality, you can immediately get a unital star homomorphism for any congruous relation like this, okay? Now, it was because of my secondment to Arizona, my and Mariusz Tobolski went to Arizona, where we were speaking to Jack Spielberg, that at a certain moment when studying some related but other things, a unital star homomorphism of that sort popped out. I mean, we're studying the contravariant factoriality of graph sister algebra. So we took an admissible graph homomorphism, and we looked at what kind of star homomorphism it induces, and to Jack's nice astonishment, it was one of morphisms of that type. Okay, and he got me excited about it. This was just one special case. It was, if I remember correctly, this was O2 embedded in M2 of O3. I believe it was something like this. Okay, but it popped up incidentally, and because we could interact during the secondment with Jack, I asked this following question. I mean, how about in general? In full generality, unital star homomorphism from OP to K by K matrices over OQ. Well, again, from K theory, we infer that such a unital star homomorphism can exist only if this congruence is satisfied. Now you see it's more complicated because you have two independent, because you have have just one independent parameter. Okay, this S. But you have three numbers, P, K, and Q, not just P and Q. Okay, and again, the story is the same. 0 must be mapped to 0. This is how you derive this congruence relation. And well, again, by Kirchbeck and Phillips, we know that they should exist, but the problem is how to construct them. Well, and the answer is provided by my very recent work with Yang Liu with CISA, but I repeat, it was inspired by Jack Spielberg and our visit to Arizona. Namely, that if you take, well, the phrase is the following, the main theorem that we have is the following here. If you take these four positive integers, P, Q, K, and S, with P and Q at least 2, and then assume that these numbers satisfy the above congruence, this one, okay? Then there exists a finite sequence of admissible graph homomorphisms, inducing injective unital star homomorphism between graph sister algebras whose composition is a unital embedding that we have, that we wanted to construct. Okay, and you see that's the art of the operator algebras that one can see, which is the title of our project. The combinatorics is given to you in a very tangible way, and it is much easier to actually discover and prove formulas. So here the magic basically happens with these three graphs. On one hand side, this is just the usual Hawaiian Ewing graph of a Kunz sister algebra. Now, that's something very easy to verify by direct computations, that this is nothing else but the graph sister algebra of K by K matrices over the Kunz algebra OM. So basically, instead of having M loops, we blow up the base vertex of these M loops into a path of length K. And when you do it, lo and behold, you get these matrices over Kunz algebra. But comparing these two graphs, En and GMK, I mean, we couldn't really find any graph homomorphisms that would induce the desired star homomorphism of graph sister algebras. Well, that's because we first had to discover something intermediate. So we were trying to collapse this graph to that graph and then use contravariant factoriality, but it just didn't work because the target bijectivity condition was not satisfied. Okay. So we came up with this graph, because here you can easily see that the target bijectivity condition is satisfied. Other conditions are very easily verifiable, so the main obstacle was this target bijectivity condition. Well, because what happens here, and now I'm using the congruence that I know that M is equal to N minus 1 times K plus 1, okay? And this is my plus 1. And I have K times N minus 1, so you can see you can see the count here. And how how do I collapse? Well, I need to be able to recover N loops, okay? And I have to do it in such a way that I have exactly as many edges collapsed as endpoints. Okay, so here you can see that I have k different endpoints from V1 to Vk, and I have n minus 1 many vertices ending at these endpoints. And I skip this one, skip this EM. Okay, don't look at it. And now basically what I can do, I can collapse these k different edges and their k different endpoints, and I can do it n minus 1 times, and then I just map EM, the last one, to EM. Okay, and this obviously satisfies the target bijectivity condition. The rest is clearly satisfied, and now I do have a unital star homomorphism from the Kunz sister algebra to this sister algebra. The problem is that it's not quite clear what this animal is. But using the technology of graph sister algebras, Rabin, Szymański, and so on, computing the adjacency matrix in the class of 1, and using Rotterdam's classification theorem, then we conclude that this is an algebra of matrices, M by M matrices over OM. So far, so good, but it's very non-explicit and by classification. But what we found is that, hey, we can go from this graph to that graph by this time using path homomorphism of graphs. And here, the only thing that you have to satisfy is to satisfy the regularity condition, okay? Now, when you look at black edges, it's no problem. I map, I mean, this edge from V1 to V2, V2 to V3, and so on. I map them to their counterparts.
Co zamykasz?
Excuse me?
Zamykasz?
Oh, I think Ludwig is not speaking to me. Okay, and now the problem is that well, how about the other edges? Well, we have to map them to paths. So when you take, say, edges going from vk to v1, well, no problem, because we have plenty of edges going from vk to v1. But now when I look at edges going from vk to v2, well, it's a problem, because I don't have any edges here going from vk to v2, but no problem, because I have paths going from vk to v2. So I just take edges, and then I compose it with this edge. And this way I have a path of length 2 going from vk to v2. And the regularity condition is satisfied because here all these edges from v1 to vk minus 1, they emit only one edge. So I always extend by all edges coming out of the endpoint. And you continue. If you want to take care of the edges going from vk to vk minus 1, well, you take some edges from here and you compose it with the path to vk minus 1. And even at the end of the day, when you have these loops, again, you can recover these loops by taking a bunch of edges from vk to v1 and composing them with a path from v1 to vk. And well, this way you have a path homomorphism of graphs, which covariantly induces a star homomorphism, unital star homomorphism of graph hysteralgebras. So now I have a star homomorphism here, I have a star homomorphism there, and I'm almost done. That's the last slide. Now I want to point to you that I can pick up some, this is elementary number theory. I pick up some natural numbers, some positive integers, and I ask them to satisfy 3 congruences. One congruence, the second congruence, and the third congruence. You'll see in a second one. Okay, so then you have the graph morphism, which I just explained on the previous page. They are all guaranteed by this middle congruence. Okay, is induced contravariantly covariant respectively unital star homomorphism between their graph hysteralgebras. So I go from Kunz to k by k matrices over Kunz OM. So from ON to mk over OM. So this is by the previous pictures, previous slide, and this congruence relation. Okay. But as Francesco pointed to me when he was visiting me in Warsaw, well, that's not the general congruence, okay? So that's not a solution. Okay, but now using Kawamura's embedding, we obtain the composite, the composed unital embeddings, because we can embed OP in ON, provided that this congruence relation is satisfied, which we assume. And here we can be, say, identity on matrices and just use embedding of OM in OQ. And to embed OM in OQ by Kawamura, all we needed is this congruence relation, but we assume it. So this way we have this composed unital embedding, which gives the desired unital embedding, unital star homomorphism from OP to MK of OQ. And here you just have to do H and D as appropriate graph homomorphisms, which I have no time to explain. And now the final thing is to verify by kindergarten number theory that if you have this general congruence, which is in our theorem, then you obtain the above 3 congruences, which we assumed to obtain these star homomorphisms, just by simply defining R to be S, L to be 1, N to be P. And here we have this tricky relation, M you have to put to be equal to this. When you do that, you see that this one congruence implies these 3 congruences. So this composed embedding exists and proves the theorem. And I find it as a beautiful application of what was one of our key research tasks in our project. And I think I'm already quite after time. Yeah, I'm 3 minutes behind the schedule. So let me stop here. If there are any immediate questions, please fire at will, but only if it's really necessary, because the next speaker should begin in 2 minutes. Any questions?
But the next speaker starts in 11 minutes, according to the program.
So I misread the time. Yes. Okay.
So we have time for a small break if you want.
Yeah, but in this case, maybe really somebody will ask some questions. Francesco, you don't have any questions?
Well, I mean, I already asked in Warsaw all the questions that I had.
Oh, Ali, you have a question. Go ahead, ask it.
Yes, thank you very much for your very interesting talk. I have a question about page maybe 17 or 18. You classified, I think this is the page. 17 or 18, you said that you classified all possible.
But I don't have page 17 or 18. I have 11 pages.
Yes,
So I don't understand.
that's the page. You classified all possible P and Q such that we have a unitary star homomorphism from OP to MK or Q. And you pointed out that you use K theory for this classification. And
Yes.
in the previous slide, you did the same for OP and OQ without
Yes.
matrix algebra. So I
Yes.
wonder if K theory itself alone can do that, because K theory is stable and it cannot distinguish matrix algebra from the algebra itself. So I wonder how K theory can distinguish the matrix case and non-matrix case.
Yeah, this is a very good question. It is true. K theory is Morita invariant. So when you take K theory of Mn of A, this is just the K theory of A. Well, and we use this Morita invariance because I know that when I look at K theory of OP, this is given to me by Z divided by P minus 1. And when I look for the other side, okay, so I will have to have a homomorphism of abelian groups, which goes from Z divided by P1, and here it goes to Z divided by Q1 because of a Morita invariance. I don't care about MK. It will always go into Z divided by Q minus 1. But you see, what is not stable, as you put it, is the class of 1. All right?
Yes,
that's the class of 1. When you look at what is the identity in this algebra, the identity in this algebra is a matrix with ones here. And when you have this isomorphism of abelian groups, is given by the trace. Okay. So basically, I know that I have one here, which goes to one there. But one there is not just one in OQ. It is one in MK of Q. So you will have K ones here, right? So this is what gives me this factor over here. It's P minus 1 times K, which must be 0. Okay,
yes,
which means being equal to S times Q minus 1. So the fact that I have matrices here is felt in the class of 1, because I not only have to have K groups preserved, but also the class of 1 has to be preserved. That's this beautiful Rotterdam classification theorem that if you have Kunz-Krieger sister algebras, if the K groups agree, then they are Morita equivalent. But if the K groups agree and the class of ones agree, okay, by this homomorphism of abelian groups, which is an isomorphism, then they actually isomorphic.
Yes, I see. And what is that theorem? The last theorem you pointed out, what is the name of what was the reference to that theorem?
Rotterdam, my brother.
Sorry?
Rotterdam.
Yes, Rotterdam. Yes.
Sorry, my Danish is a bit rusty. David, can you
No,
correct?
that's good. That's good. Yes. Yes, I see.
Yeah.
Thank you.
Sure. You are most welcome. Okay, we have one more minute. Anybody else? I don't know. Tomek? You always ask questions. David?
I'm good.
Yeah, go ahead.
No, I'm good.
You are good.
Yes.
So maybe I can make a short comment that
Yes.
with Atomic, we had a similar problem that we find when we tried to construct a multiplicative version of K-theory. We had this problem that it was not Morita invariant. And it was not Morita invariant exactly for this reason, because in the construction of this multiplicative structure, we used the class of 1. And that depends only on the Morita equivalence class of the algebra, but actually on the isomorphism class. But then this, Tomek, this maybe could be a feature, not a problem. I don't know. Okay, this is sorry, it's not
It's a
related.
feature. It's a feature because you can introduce some kind of Morita equivalence of Hopf-Galois extensions.
Yeah.
And then from one Hopf-Galois extension, you obtain another one, but you don't have a map. You have something like a functor between categories of modules.
Yeah.
And then you can accommodate in our construction also these more general correspondences between spaces than coming from homomorphisms of algebras. But of course, if you are interested in classifying algebras up to isomorphism, keeping track this one is very important. Yeah.
Okay. So since the time is up, let me answer the chat question. So will the recordings be uploaded? Yes, they will be automatically by the Banach Center. So go to the conference homepage and they will be appearing on the fly. And Ralph, I'm sorry, I don't know if my morphism preserve a canonical Cartan subalgebra, but maybe we can discuss it some other time, okay?
Well,
So
the U1 equivariant, it should, right? One of the two is always U1 equivariant. So for that,
that's
is
true.
automatic. The other, maybe.
The other, yeah. Okay. So I stop sharing, and David, start sharing your slides. And we have 4 minutes.
Thanks again for your talk. It was very beautiful.
Thank you.
Piotr, if I may say something following your
Yes,
lecture on the secondment, I wanted to apologize, for not using so many secondments. It was because of the war in Israel that we
we know, we mentioned it, yes.
Really use them, but there are 3 secondments at least planned for the foreseeable future. And we have 3 papers just from the group in Haifa for this grant, just to let you know, yeah?
Yeah, this is wonderful. And I also very much like interacting with your postdoc. What's his name?
Lucas
Hall.
Hall. Yes, he's also involved in this, indeed.
Yeah, that this is really makes me very happy.